Okay, so the last video we were talking about fractions and fractions following fractional distillation of crude oil. And remember, the definition of a fraction was like a mixture of chemicals we got with similar boiling points that we got from the process of fractional distillation. You can look back at the last video if you want. But this video I want to talk about what are the molecules within each fraction. What are the molecules, what size are they, what kind of properties they have, etc. Because they are the useful chemicals we use in our world. Before we do that, let's sort out some terminology issues. I want you clear on the following terms. Firstly, a molecule. Well, a molecule is a collection of atoms covalently bonded together. And we're going to be talking about molecules. So I'm going to be holding up models like this. Sorry, I've got the remote control in my hand here, so I might have moved it on. But I'm going to be holding up models like this. Look, this is butane, 4 carbons long, and that is a molecule. Molecules are atoms covalently bonded together. So there are 14 atoms there. There's 4 carbons and 10 hydrogens. The hydrogens are white and the carbons are black. And the purple bonds are the covalent bonds. So where you've got covalent bonds holding together, in this case 14 atoms, that whole collection, a collection of atoms covalently bonded together, that is a molecule. Now, I'm going to be talking about different fractions have different molecules. So different fractions have different things like this. And there are bigger molecules and there are smaller molecules. And as I say, we'll be getting back to it. But be clear what we mean by a molecule. It's a big problem I find is that boys don't really understand what the word molecule means, and they use it in the wrong context. Anyway, let's move on. Fraction. I told you about what a fraction was last time. It's a mixture of chemicals that you get by fractional distillation, and they all have the same boiling points. They are the chemicals that are within that fraction. So one fraction, like petrol, is a mixture. It's a mixture of liquids that all have similar boiling points that you've got by carrying out a fractional distillation experiment. Hydrocarbon. Well, these are compounds that are made of hydrogen and carbon only. Now, all of those terms we've come across before. I'm recapping them so that you understand what I'm about to say. Before we get on to the nitty-gritty of what I'm about to say, let's go over what we mean by formulae or formula. Formula singular, formulae plural. Empirical formula. The empirical formula is just the simplest whole number ratio. Simplest whole number ratio, like water, H2O. You can't get more simple than 2 to 1. So for an example of that would be if we had CH2O. Now, that's the simplest whole number ratio formula. Well, what's molecular formula? Well, molecular formula is talking about molecules. And when it talks about molecules, molecular formula talk about how many atoms of every element in each molecule. So the molecules are these things. How many carbons? 4. How many hydrogens? 10 hydrogens in one molecule. that collection, they're all covalently bonded together. So a molecular formula is the actual, and that's the key word, actual, the actual number of atoms of each element present within a molecule of the compound. And say we had this as the empirical formula, well, the molecular formula might be that in every molecule there are 2 carbons, 4 hydrogens, 2 oxygens. Well, clearly, if you've got 2 carbons, 4 hydrogens, 2 oxygens, they can be arranged in different ways. And if you arrange them in different ways, for example, you might put 1 carbon with 3 hydrogens around it attached to a COOH group, and that would make it ethanoic acid, which you need to know about. It's a famous weak acid. It's vinegar, in fact. That acid has got that structural formula. The idea of structural formula is that it will tell you, the structural formula, how the atoms are arranged in a pretty obvious way. It does not have to be longhand. It can be shortened, like that CH3 is short for having a carbon with 3 hydrogens around it, CH3. But the best formula of all, the formula which tells you everything about the chemical in question, is displayed formula. And the displayed formula is a formula which shows every covalent bond present. And that's a displayed formula for vinegar. That's a displayed formula because it tells you exactly 1 covalent bond there, 1 there, 1 there, 1 there, 2 there, between that carbon and that oxygen, 1 there and 1 there, and that is, the displayed formula is unambiguous. Displayed formula shows every covalent bond. If you leave 1 covalent bond out, you don't draw it in, then you fail as a displayed formula. Displayed formula has them all in. Now, that structural formula does not have to have them all in. It just is a shorthand way of showing the structure. The molecular formula is simply telling you how many atoms of the different elements within every single molecule. And the empirical formula is the simplest whole number ratio. So let's see if this is consistent. Simplest whole number ratio, if you double it, C2, H4O2. That is the molecular formula for, that's the empirical formula for ethanoic acid. For vinegar, that is the empirical formula there. That's the molecular formula there. That's the structural formula. And that's the displayed formula. And all of them relate to vinegar or ethanoic acid as the chemical that we're talking about on that slide. But the ideas that I've talked about with ethanoic acid can be applied to anything. We can write empirical formula, molecular formula, structural formula, displayed formula. And we're going to use these terms at GCSE, so get used to it. When we talk about chemical formula then, that's a bit vague. With chemical formula, you never know what it is to write. Well, if they say molecular formula, you know. If they say structural formula, you know. If they say displayed formula, then use the sticks to show every covalent bond that's there, and so on. Right, so what molecules are there within the fractions? Well, inside the fractions, you find hydrocarbons. So molecules that contain hydrogen and carbon only. They're the common things we find in our crude oil fractions. Remember the gases, petrol, naphtha, kerosene, and so on, the 8 fractions? Well, they're all hydrocarbons within the mixtures. What's common in every mixture, every fraction, is similar boiling points. And you've got them through fractional distillation. Hydrocarbon molecules always have every carbon with 4 covalent bonds. Look, here. This is the smallest of my hydrocarbons. 1 carbon, 4 hydrogens. Now, that 1 carbon, 4 hydrogens is symmetrical. It's more or less an equilateral triangle on every face. If you join up the white balls, join them up, you get a solid shape, and that solid shape is called a tetrahedron. That is tetrahedral in shape. It's shaped around a tetrahedron. The bond angles, that bond angle there, for example, that one, there to go that way, that bond angle is 109.5 degrees. How do I know that? Well, I know my angles of a tetrahedron. They're 109 degrees, 28 minutes. So I want you to know that that is a small molecule. That is a big molecule. They're both hydrocarbons. Different molecules are hydrocarbons because they both contain carbon and hydrogen only. And every time we have such a molecule, there are some rules that you must never break. So carbon always has 4 bonds. Hydrogen always has 1 bond. Oxygen, if it's present, has 2 bonds. Let's go back. Look, carbon, it's got 4 bonds. 4 bonds. Oxygen, 2 bonds. 2 bonds. Every hydrogen, 1 bond. So these number of bonds are what we call them valencies. And the valencies of carbon are 4, valency of hydrogen is 1, valency of oxygen is 2, and valencies is the number of bonds that something will form. So let's try and draw some molecules that we might find. So what molecules might you find within fractions? Right, I think this is me writing. So the smallest hydrocarbon. Now, this is a point I want to make. If you've got this, 1 carbon, 4 hydrogens as a molecule, how do you show a 3-dimensional shape on paper, which is 2 dimensions? And we might do that. That is CH4. CH4 is the molecular formula. That is the displayed formula. And this is a model using the molecular model kits that we have. And they're all ways of representing methane, which is the smallest hydrocarbon. It's the molecule or the chemical that's in natural gas that your boilers need or you do your cooking on, etc. What's the other, or what are other hydrocarbons? Well, they're just longer. So 2. That's a hydrocarbon. That's not a normal hydrocarbon though. That's got a double bond there. And the double bond there makes it something different. But this, that, 2 carbons long, that is that. Don't know if you can see that. And CH3, C, carbon there, 3 hydrogens, the white balls, and 1 carbon, 3 hydrogens next to it. And with that, you can get rotation. These bonds, the molecules can move, they can rotate. That's why we like the models. The models tell you how the molecules might be able to move and behave. And you can get rotation. If I hold it like that and show you, this can rotate around about the carbon-carbon axis. And that's important because when you start drawing these molecules, I don't want you to make a mess of your drawings. Right, so my thing stopped working. My pointer has stopped working. All right, I'm going to have to press a button here. So let's talk about having one carbon. One carbon, 4 hydrogens. Methane. 2 carbons, 6 hydrogens. It's called ethane. 3 carbons, 8 hydrogens, called propane. 4 carbons, 10 hydrogens, called butane. Methane, ethane, propane, butane. Can you see a pattern? The pattern is that every member within that group is 1 carbon bigger and 2 hydrogens bigger. Basically, a molecule like that, if you pull it apart and put an extra carbon in between with 2 hydrogens. If you put one of those, a carbon and 2 hydrogens in between, then you can make something which is 1 extra carbon long. Look, 3 carbons. 3 carbons there, that's an extra carbon. And you can carry this process on. There, I've got 4 carbons. Butane. Now, there is a way to name chemicals, and I'm going to go through naming in a minute, just very briefly, but molecule like this, I want you to know you can rotate these things round like that. And so when you're drawing it, we tend to draw them in a straight line, but they're not really in a straight line, they're kind of zigzaggy. The molecules are in fact zigzaggy, but we don't draw them zigzaggy, we draw them as though they are straight chains like that. And that's not right. It's not right, but it's something we do, and you're just going to have to get used to it. Something that we draw in a straight line is in fact not a straight line. Well, that's the problem of trying to show a real molecule using either a model or using paper, which is 2-dimensional. It's the limitations of our representation that we have in a 2-dimensional space like paper. Anyway, I'm getting fixated on something. Let's move on. Can you see a pattern between methane and ethane and propane and butane? The pattern is that for every carbon, if carbon is 1, C1, the number of hydrogens is double it, add 2. C1, H double it, 2, add 2 is 4, CH4. What if N is 2? If N is 2, H double it, 4, add 2, 6, C2H6. How about if you've got 3 carbons, with 3 carbons, you'll have C3, H double it, 6, add 2, 8, C3H8, C4H10. The general formula of these things is CnH2n plus 2. And that family that I've tried to develop with you, starting with 1 carbon, and then 2 carbons, and then 3 carbons, and then 4 carbons, and going on and on and on, that family is called the family of alkanes. Now, the word family is an Ahmed word. I've just made it up. Not a family at all. It's a series. And when we have these families, and there are 4 families we're going to discuss, the families are alkanes, alkenes, alcohols, and carboxylic acids, but the 4 families, the chemistry name for them is homologous series. So there are 4 homologous series we're going to discuss. And within every homologous series, like this is the first of our 4 homologous series, we're going to, with each one, talk to you about the smallest and the next and the next and the next, and give you like a general formula and tell you what's unique about that homologous series. Now, what's unique about this is that all the bonds are single covalent bonds. Each one of these is a single covalent bond. You don't have any of these. Now this, what I've got here, is a double covalent bond. It's a carbon with 2 bonds between them. Now when you have a double carbon bond there, then they're called alkenes. And alkenes are defined by their double bond between carbon atoms. Well, alkanes don't have those. Alkanes, every bond is a single bond. So the first family, the first homologous series I want you to know about is alkanes. And where are our alkanes? They're inside our fractions. The crude oil fractions are largely full of alkanes. The ones at the top, the fractions at the top of the fractionating column, have small molecule alkanes, like the smallest one, like methane, whereas the next fraction down, petrol, has alkanes that are like 8 carbons long. And the further down you come, that fractionating column, the longer and longer chains you will have of carbon atoms. And when you're down at the bottom with fractions like bitumen, then bitumen has like not just 4 carbons, but 50 carbons. Really long chains. And around, say you got a carbon with 50, how many hydrogens would it have around it? Well, double it, 100, add 202. So it'd be C50H102. And that would be coming out of the fractionating column much lower down, because its boiling point would be higher up, being such a big molecule. Let's move on. Right, okay, so my this pointer started working good. Now, this series of molecules, that homologous series I've been talking about, is known as the family of alkanes. And alkanes are just one family of common compounds. The chemistry term to use is homologous series. So use homologous series, please. What is the definition of a homologous series? Well, the definition is it's a series of molecules. Now, they're all the members within a homologous series, all of them will behave in a similar way. So the chemistry will be similar. The reactions will be similar. But you can't say that same thing about physical properties. So the chemical properties are similar, but the physical properties, like boiling points, just get bigger and 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 bigger. And like that, you can't say similar. You have to say a trend. The trend is they get bigger and bigger and bigger and bigger and bigger and bigger. And you must use this terminology. Similar chemical properties, that's supposed to be and a trend. And a trend in physical properties. Yeah, that's a typo. It should be and. So learn that, please. Learn that's in red. Learn that. Homologous series. They ask it on exam papers and you need to know it. So, crude oil is largely a mixture of alkanes. Methane, the smallest one. That's the one that I was holding up here, that one. That's tetrahedral. Ethane is 2 carbons. Propane, 3 carbons. Butane, 4 carbons. General formula CnH2n plus 2. Similar reactions, trend in physical properties like boiling points, diffusion rates, masses, that kind of thing. So trends in physical properties, as the molecules get bigger and bigger and bigger and bigger and bigger, then you have these trends. As the molecules become bigger, their boiling points increase. So those fractions, if you look at the molecules within the fractions, then as the molecules get bigger and bigger, their boiling temperatures get more and more. They increase. and we collect them lower and lower and lower within our fractionating column. Now we have to explain that. So let me try and explain it to you. There are two main reasons, and both of the reasons are based on the idea that the molecules are simply getting bigger and bigger and bigger and bigger. But what is it about the size? What is it about them getting bigger that leads to increased boiling and melting points, etc.? Well, firstly, you need to know about mass. So if you've got a bigger molecule, it will weigh more. So if the mass is more, the proper way to say in science is, if the mass is bigger, then you'll need more energy to get it to move. And to get it to move, if it requires more energy, you'll need a higher temperature to do so. So that's reason number one. The second reason is, the bigger molecules have more attractions between the molecules. Intermolecular means between molecules attractions. So they have more intermolecular attractions, and because they've got more attractions, then you need a higher temperature to overcome them. So that's why as you go down the fractionated column, the molecules have bigger boiling temperatures. As the molecules become bigger, their viscosity increases. Now, if you remember, viscosity is about how thick and gooey something is. And the thickness or the gooiness of something is how the molecules can tangle. If there's lots of tangling, like, look, I've got a long molecule here, hexane. If there's long molecules, there's more scope for tangling to happen. If there's more tangling that happens, then what you'll get is, function of the more tangling, it'll be viscous, it'll be thick and gooey. Like treacle. Molecules are big. I don't know what's in treacle, but I'm telling you that the molecules will be big, there will be tangling to give treacle that kind of like thick gooiness that when I use treacle to make my sticky toffee pudding, it is thick and gooey. 3. As the molecules become bigger, they become more difficult to burn. I remember showing you a slide in my last video where there were trends as you went down the fractionated column. And this number 3 is another one of those trends. They're harder to burn. Now, if you and I know that burning is a reaction with oxygen, then if you've got big molecules like this, it's harder for the oxygen to get to every atom. And if the oxygen finds it hard or harder to get to the atoms, if the oxygen can't get to the atoms as easily, then they're going to be harder to burn. The burning reaction is with oxygen, and therefore the ability of the oxygen to get in is paramount. So let's have a look at what I've written. So as the molecules become bigger, the viscosity increases, the bigger molecules will tangle more with each other, leading to increased viscosity. Molecules are bigger, they could become more difficult to burn. For bigger molecules, it's harder for the oxygen molecules to get into the molecules for the reaction to take place with the atoms within the molecule. So I hope I've verbalized in text, red text, what I've tried to explain using my language. As the molecules become bigger, they're collected further down the fractionated column. Well, I think this is pretty obvious. It's all about boiling temperatures. The boiling temperatures are bigger if it's a bigger molecule. And the temperature lower down is a bigger temperature. So the bigger molecules with higher boiling points will condense lower down the fractionating column. Bigger molecules have bigger boiling points, and so they'll condense further down the fractionated column where the temperature is hotter. Now, those trends, I suggest you learn the right phraseology to answer those kind of observations that I've tried to address in red text that I've written myself. Finally, the molecules need a discussion about isomerism. Now, isomerism, it's getting a bit dark. I'm just going to turn the light on 1 minute. Right, okay. I hope you can see me a bit better now. Isomerism, final discussion. Well, isomerism is about having molecules that have the same molecular formula but a different structure. So if I hold up something like this, hexane. It's called hexane because it's 6 carbons. 1, 2, 3, 4, 5, 6 carbons. And if I add up the hydrogens, 14. Double it, 12, add 2, 14. 14 hydrogens. Now that is a molecule. If I change it, that's the same molecule. Molecules can bend and twist and they can go round like that. Almost like forming a hexagon. Or they can be in a straight chain like that. Well, you can't get ever a straight chain. What you can get are these zigzags, like that. But they're all the same molecule. They're not different. Isomerism is, can you use the same atoms and get a different molecule? Something with a different structure. And what I have an Ahmed word I use, which I want to convey the right idea to you in your head. And that is the sequence of links. I call it linkaging. The linkaging has to be different. Now, by me doing this, I haven't changed any linkaging. With me doing that, the linkaging is the same. That is not any different molecule. But if I were to snap that off and snap that off, and put that there, I've taken out the middle bit, snap that off there, put the carbon there instead, that hydrogen I've got, I put on there. Now that is fundamentally 5 carbons in a straight chain there, with 1 carbon as a branch. And that's fundamentally different. The linkaging is different. Where the linkaging is different, then that's an isomer. Now we can't go around using Ahmed words like linkaging. We have to use normal words that are in the chemistry syllabus specifications. So the words I want you to use are, these are isomers, and the definition of isomers is where we've got different molecular structures with the same molecular formula. Let me say that over and over again. The molecular formula has to be the same. That means same number of carbons, same number of hydrogens, etc. So the numbers of carbons and hydrogens or oxygens and fluorines, whatever you might have in a molecule, that's reflected in the molecular formula. And once you've written that down, you must stick to it. You must get exactly the same number of carbons, hydrogens, etc. and arrange them differently. Link them differently. And that, in a chemistry setting, is called structure. So when we've got different structures, here look, 4 carbons, 10 hydrogens. 4 carbons, 10 hydrogens. 4 carbons in a straight line is butane. 3 carbons in a straight line with a branch is methyl propane. They are isomers. The linkaging is different. The structures are different. The molecular formulae are the same. Where the molecular formula is the same, structure is different, they are isomers. And one of the questions you get is, can you draw different isomers? Well, with butane, there are only 2 isomers possible. With 4 carbons, there are only those 2 structures possible. But what if we have something like that? 6 carbons. Then obviously you're going to have many, many more isomers. And if we draw them, you'll have these. You'll have 5 of them. Can you see? Do not just draw differently by flipping these round. You must fundamentally check that the linkaging is different. Now, isomer number 1 has the 6 carbons in a straight line. Isomer number 2 has 5 in a straight line, and 1 carbon is a branch. 3 is 5 carbons in a straight line. Now the branch is in the middle, whereas it's not in the middle there. Number 4 is 4 carbons in a straight line and 2 branches. Each branch is a carbon off it. And number 5 is 4 carbons in a straight line where the branches are coming off the same carbon. All of those, trust me, on the board are different. The linkaging is different. The structures are different. But each one has got 6 carbons, 14 hydrogens. That's what makes them all isomers. So hexane has 5 isomers. And practice drawing isomers. The problem with you practicing drawing isomers is you normally draw the same molecule just looking at it in a different way. Like that. Say you're asked to draw hexane. Now that is methylhexane, and people think that is different. It's not. That is different. It's not. They're all the same. Those 3 on the board are the same. Why? Because their linkaging is the same. If the linkaging does not change, then I'm sorry, you won't have isomers. You have to change the linkaging. Or the proper way to say it is, the structures have to be different. Those 3 on the board, the structures are the same. So isomers, the structures are different. These are all the same. Now, if you imagine this one, pick it up, flip it over, that's just that. If you take that and do that, that's just looking at it in a different way. This one is doing like the bending it round. If you bend that round, but fundamentally a carbon with 3 hydrogens, carbon with 3 hydrogens, carbon with 2 hydrogens, carbon 2, just follow it. Carbon with 2 hydrogens, carbon with 2 hydrogens, carbon with a branch, carbon, there's the branch, leading on to another carbon with 3. Check the linkaging. It's all about linkaging. It's all about structure. The structure has to be different. And you're just going to have to practice drawing isomers, and your teacher telling you that you're a twazzock because you've drawn the same structure and not anything different. So finally, do isomers have the same boiling points? Well, no. Isomers can have different boiling points. So we're talking about things with the same size, same number of carbons, hydrogens, etc., but different boiling points because their shape is different. Now here we've got sausage-shaped molecules, 1, 2, 3, 4, 5 carbons. That would be called pentane. Now pentane, if you've got normal pentane like that, they're sausage-shaped molecules. And you can get attractions across their surface area, and the attractions, you'll have more if the molecules are sausage-shaped than this one's got 5 carbons. The linkaging is different. That was an isomer, C5H12, C5H12. But these molecules, I hope you can see, they're more ball-shaped. They're more spherical. And when they're more spherical, I tried to draw a second one, but I ran out of space. But if you draw a second ball the same size, you get less surface area interaction if the molecules are ball-shaped. So where you've got isomers like the same size, but some are ball-shaped and some are sausage-shaped, the sausage-shaped ones tend to have a higher melting and boiling point than the ball-shaped ones. Now again, we don't say ball-shaped. What we say is, we say more branching. When you have more branching, then the boiling temperatures are lower. Where you've got less branching and more straight chains, then we say the boiling points are higher. Now, isomers of pentane. There are 3 of them, look. 5 carbons in a straight chain. 4 carbons in a straight chain with a carbon off. 3 carbons in a straight chain with 2 carbons off. The reason I got the slide, I think, was to give you boiling temperatures. This straight chain, the boiling temperature is highest. That's more ball-shaped. The boiling point is lowest. This is intermediate between the two. The boiling temperature is between that and that. For you to see a little bit more clearly, this 4 carbons with the methyl here is exactly the same as this. 4 carbons with the methyl here is exactly the same as this. 4 carbons with the methyl here is exactly the same as that. 4 carbons with the methyl here. They haven't drawn the other hydrogens in on those 4. But it's just a slide to get you to think about branching. Branching gives you less attractions between molecules and the boiling points then become lower. Straight chain isomers have increased melting and boiling points compared to their branched isomers. Sausage-shaped molecules attract each other more as there are more intermolecular forces that attract the molecules, leading to increased melting and boiling points. Whereas ball-shaped or branched molecules are more spherical and so attract each other less, and these weaker attractions between the molecules are responsible for lower melting and boiling points. So the shapes of these things, if they're the same molecular formula, the shapes of these things, the shapes of the isomers, fundamentally will affect the melting and boiling points. I hope now you know how it will affect it. All right? Okay. So that's it. I'll see you next time.